esters, the named amides, and we now are, let's see, we pulled this off, right? Make salt, so we should be here at the hydrolysis of amides. Make sense? So if you hydrolyze anything, it'll all go back to a carboxylic acid. Well, not anything, but if you hydrolyze an ester, you get the carboxylic acid. If you hydrolyze an amide, you get the carboxylic acid. So everything goes back to the carboxylic acid in terms of the derivative. All right, so what you're really looking at here is the fact that hydrolysis, amides will undergo a base hydrolysis. That means we're going to do it in the basic solution, so we would end up with an O- and an Na+. That would then be the salt form. Acid hydrolysis would also leave you with the regular carboxylic acid and amine. I don't know that that's the great slide. I'd rather look at that than actually just try to see that work. So if I'm taking, for example, this is going to be an acidic hydrolysis. What I'm really going to do, and this is just not what you need to know. I mean, what they want you to know is that if you do acid hydrolysis, you get the carboxylic acid and an ammonium chloride. Now, what really happens here is this nitrogen right here has a lone pair on it. That is less electronegative than the oxygen, correct? So this nitrogen is going to pick up this acid. That makes the ammonium. When this nitrogen picks up the hydrogen, this then becomes an NH3 with the plus and the Cl. Okay? Does that make sense? At that point, this plus charge begins to pull electrons away, and so then the water comes in and kicks that out, and that's how you get the carboxylic acid and the ammonia. Okay? So it is just like all the other reactions if you're looking at the electron flow, but your book doesn't necessarily talk about that. It just says, well, this is right out of your book. And this is why I'm like going, yeah, that just about drives me nuts. And it is the idea of acids will undergo acid hydrolysis and base hydrolysis. Acid hydrolysis will give you a carboxylic acid and ammonium salt. Base hydrolysis gives you the carboxylic salt and an ammonia, amine. That's just weird to memorize. It's just weird to memorize. So, here is what's happening here, but this is the why. I have a lone pair here, and this chlorine is pulling electrons away, partial positive, partial negative. So this is going to come in and pick that up. That means I'm going to turn into NH3. I can put it up here if you like. NH3 with a plus charge and the Cl minus. Or I could choose to draw it just like NH3 plus Cl minus. Now at that point I only have water left, which comes in then and knocks that ammonia out. And so I end up with the carboxylic acid and the ammonium chloride under acidic conditions. Here's a little help that works. Under acidic conditions, you're not going to have a negative charge because you're in an acid, which is an H+. So you would end up with either no charge here and no charge here, or a plus charge. You either end up with no charge or a plus charge. Let's see if basic hydrolysis is next. Nope, that's still acid hydrolysis. Give me basic. Okay, I'm just going to give you basic hydrolysis. If I do basic hydrolysis, that means then I don't have this and I don't have this. What I do have is an HO minus, and it would actually be an NaOH, Na plus HO minus, sodium hydroxide. So this will come in here and kick that out, which means then I have CH3, C double bond O, OH, plus then NH2. And this NH2 will actually pick up that hydrogen there because it's acidic and form then the NH3 plus Cl, but that would then be the salt here. Okay? That would be the salt there. That's what those words are trying to say. So if this is me, I would probably, if this was my study guide, I would take these words and I would put the one word on this slide so that I see that, okay, visually, you're right. Oh, there it is right there. Never mind, I did that for you. Hello. Yes?
So when, right, lone pair from my goes and grabs the hydrogen from HCl, he comes to NH3 plus and Cl minus. Where does the NH4 plus come from?
So what's going to happen, yes. So what's going to happen is as the water comes in and kicks it out, the water still has its two on there. And so this is going to come in and pick up another one off of there to get the NH4 plus.
Wouldn't that give it 2 plus charges because it was already NH3 plus?
But so let's do this. It's a good point. Very good point. So here, prior to kicking it off, if I have NH3, okay, prior to kicking it off here, I have a nitrogen that brings how many to the table? 1, 2, 3, 4, 5. Okay, and so it owns how many? It owns 1, 2, 3, 4, right? So it owns 4. 5 minus 4 equals plus 1. So it has a plus charge here. When it leaves, it is an NH3. Because when it leaves, it takes these electrons with it. Okay? Now how many does it have? None. But then, when it comes back up and picks this up again, now it's the 4, and it has that charge again. So charges are transient, and it's what drives reactions. That's why you see me push electrons and keep track of those charges, is because that's really what drives that electron. It's easy enough to... I wouldn't do this except for this page is just, for me, confusing to say, if I undergo an acid hydrolysis, I form the carboxylic acid and an ammonium salt. Awesome. There, I just did that. But if I undergo basic hydrolysis, I form the salt of the carboxylic acid, which then would be an O minus, and the amine or the ammonium. Either one. And I couldn't find one in your book, but I'm hoping that it comes up. There it is, right there. So here then is the basic hydrolysis. And this is kind of what's happening here. As I kick this out, this comes in and picks that up, so I form the salt, Na here, and the amine or the ammonium. So there's that salt. And that would come from NaOH. This reaction just doesn't have the plus charge in it. But every time you have a negative charge, you have to have the corresponding cation that goes with it. And that would be an Na plus. Yes?
So the slide said that it involves the base and water.
So, yeah, so this is a solid here. And so it's made by dissolving it in a water solution. That's an 1110 thing. And this is interesting in that all of a sudden, you're taught in a memorization fashion, and you're expected to remember that. Did you remember sodium hydroxide always had to be dissolved in water? I know I didn't. Until I realized that it's a salt. Sodium hydroxide is a salt, just like sodium chloride. Everybody has experience with table salt, and sodium hydroxide looks just like table salt. You can't tell the difference. Well, if you taste it, salt tastes like salt, and sodium hydroxide tastes like Drano. Because it is, sodium hydroxide is the Drano that you put down the drain to unclog it. So here is, so again, you know, to me, what would be easier, and I guess if I was to do this again, I would almost just get rid of that because it kind of drives me nuts. I can see it here, and then I can see it here as well. Okay? Yes?
Can you go through a base hydrolysis?
Yes. So what happens here then is the base comes in, okay? The base comes in and kicks this out. So this becomes an N minus, okay? So what happens then is this N minus, and this is going to become an OH. So what happens then is this N minus here, which in this case doesn't have the methyl group, but in here it does. This is the other thing. The reason that we have two of these is because you get used to just seeing this, and then when you see this on a test, you don't know how to apply it. But it's got nothing to do with what it drags with it. This is just the ethane, methane, propane, butyl, butylamine, ethylamine, propylamine, so on and so forth. So in this case, this is the N minus, and when this comes in, it's an OH, but then the N minus picks up the H to become the NH2C3. So this is the real answer to your question, is just adding then the methyl group off of this or whatever else you see. Now I see a bunch of frowning eyebrows out here, so let's start asking questions. So my sodium hydroxide, so here's kind of a different, let's approach it this way. When you look at the acid here, you really need to, this is my strongest Lewis base. This is going to pick up this hydrogen. Now that this nitrogen has a plus charge on it, okay, that makes it capable of leaving. But what do you have left? See, so if I pick up this, this becomes an H3 plus. This is water. You bathe in water. So water is not a good, strong Lewis base whatsoever. You bathe in it. But this is now has a plus charge and is trying to pull electrons away so that this is going to come in and kick that out. And when you have that, you end up with this guy right here. And so the nitrogen, the NH3 that you just picked up, picks up one of these hydrogens, converts this into the OH, and then this turns into the NH4Cl. Okay? That's the acid hydrolysis. And that fits that it involves an acid and water, produces the carboxylic acid and the ammonium salt. You see, that's what your book wants out of that, is the carboxylic acid and ammonium salt. Me, I'd like you to have that because the book wants it, but I'd like you to understand it a little bit more. So if we then go to the base here, now this base is Drano. Nobody bathes in Drano because Drano chews up your hair, it chews up your tissue, it chews up everything that you spit down the drain. That's its job. So this thing is not going to wait around for the nitrogen to protonate. This is a full-blown OH minus. That's a strong Lewis base, so it's going to go in and just kick this out. That means that when it kicks it out, I, in this case, am an NHCH3 minus. Okay? 1, 2, 3. That means I actually probably have 2 electrons there. Yes, there I do. All right. Now, these look different, and that's an important distinction. They look different because your book or an exam can give you any number of amine-looking compounds. The real focal point is the nitrogen connected to the carbonyl. That's what gives it its amide name. Okay? So this is what you're kicking out, and when you kick it out, these electrons are going to come with it, and that means it's a minus charge. So when this gets kicked out, same thing with here, the OH goes into there, and now I have a carbonyl next to an OH, there it is, and then this nitrogen minus, which is this guy here, picks up the extra hydrogen, and that's how you then get what this gives you is the carboxylate, the carboxylic acid, salt of the carboxylic acid, and the amine. So this being an O should have the Na plus here. Right? Now, this comes out of your book suggested PowerPoints. If this is me, I've given you access to go in here. I would add the Na plus right there just so it matches what it says. But that's homework for you to do because then that tells me that you know how to do that. If I just put that right there, that would just be a visualization and you would ignore that. But now that we've had dialogue over it, you'll go in and put that and it'll make more sense. Yes?
So it doesn't turn into kind of a true carboxylic acid because we don't have any hydrogens to...
Exactly right. It turns into a carboxylate, which is a salt of the carboxylic acid. Absolutely. Very good. In a basic solution, you end up with a negative charge or no charge. In an acidic solution, you end up with a plus charge or no charge. Because a base brings in a negative charge, and an acid brings in a plus charge. So in an acidic solution, you either end up with a plus charge or no charge. In a basic solution, you either end up with a negative charge or no charge. And that will be the case for all acids and bases. So this is then the explanation of, if I have acid hydrolysis, I end up with the carboxylic acid and an ammonium salt. Under basic hydrolysis, I end up with the salt of the acid and a regular amine. So they're different, right? There's the acid, I get the acid and the amine, and here is the base, I get the carboxylate and the amine. Any questions there? The nice thing is there's very few reactions in this chapter. It's kind of nice. So one of the other reactions that you can undergo, if you look at this right here, okay, I have an amine, and I'm using an acid, and I'm bringing in water. This is the one we just looked at. Okay? I'm bringing in water. So I'm going to make this a plus charge, and my water is going to come in and kick that out, and I'm going to end up with this thing right here, and then this NH3 will pick this up right here, and that then makes my ammonia, and it makes my carboxylic acid right there. Is everybody okay with that? Now, let's change that a bit so that we can see how these other ones. What if I change this from just water to water's bigger cousin, an alcohol? Do you think anything changes to how this occurs? Only thing that changes now is I'm going to have this attached to this part here. And so that is one of your reactions. So your reactions of amides are to protonate this and then bring something else in to kick it out as an ammonium chloride. Okay? So this is, in all reality, if we asked about this a little bit, who do you think can give more electrons away to an oxygen here? A hydrogen or this alkyl group? The alkyl group will give more hydrogen. So this is actually, this reaction goes a little bit better than just the water. You see, nobody's going to bathe in Everclear, in ethanol. Nobody bathes in ethanol because it is a stronger, you are? Not on the outside, but on the inside, often we do, yes. So this is a telltale sign that this is a little bit stronger of a Lewis base than the water is. The water we can just sit in forever, but this would begin to start to do reactions. Yes?
So, the chain one with the alcohol, is it no longer a carboxylic acid?
That's exactly right. It's no longer carboxylic acid. Remember what we named? It was the ester. This is the propyl ethanoate that we named. So this is this guy right here. One of the reactions, acid reactions, that is related is instead of water and hydrochloric acid, we added an alcohol and hydrochloric acid. So instead of just getting the OH or the carboxylic acid, we get the ester. What I'm trying to show you here is we're doing the same thing. So it's not something new. Because when you memorize this, it's just an insurmountable amount of things to memorize. It's hard, it's difficult. But if you can see the relationship and say, well, yeah, this picked this up so that left and brought in the water. Oh, but that looks like water, so I probably bring that in too. And absolutely, you've made the ester. So that's just some of your, that's just a reaction off of the hydrolysis. But, so here's your learning check. Write the equation for hydrolysis of, ew, gag, N-ethylpropanamide. Everybody know how to remember? That was a long weekend. It was a short, long weekend, I get it. But it was long enough for us to go, wait, how do we do this naming? Remember the name of the ester comes first. So in this ethyl, N-ethylpropanamide, the hardest part, I think, of this is actually drawing this out. This would be, so let's look at it from a naming standpoint. N-ethylpropanamide. So I'm going to go, here I go with my amide, and this is a propane. 1, 2, 3, okay, propanamide, and I have an, on the N is an ethyl. So this is N-ethyl propanamide. Probably some of the weirdest nomenclature you've ever run into. And you might like to see it like this.